Okay, so today what we're going to be talking about are maximum entropy distributions for continuous probability distributions. So previously we've talked about this in the context of discrete probability distributions where we had a discrete number of events. So now we're going to look at the corresponding concept for the case of continuous variables. And now this is kind of it's not just a fun exercise for us to do. It actually comes up because, as you might see later in the book, often you have some information about a probability distribution that you're interested in. For example, as we'll see, let's say you know that you have a continuous variable and it has a certain mean and a certain variance. And now the question is, what is a suitable prior to put on that variable for you to then do additional inference with it? And there's a guy called Ed Janes, and I'll put a link to him in the description. And he argued that what you should do in those situations, and I think it makes a lot of sense, is to use to essentially say that you have maximum uncertainty given the information that you have. So if you need to put a prior on this, on this random variable, and you know that its mean is whatever it is, and the variance is something else, well, then the prior you should have on that random variable is the maximum entropy distribution. So the distribution where your uncertainty is as high as it can be, given the piece of information that you have. So these are called maximum entropy priors, and they have some nice justifications like I've given you. So that's kind of one area where they come up, and so it's useful to know how to compute them. So we're going to do that today. So here he just kind of outlines the approach. We'll actually do the computation. He says that we need to do it with using the calculus of variations, and I will show you that at least in this particular case, we don't. We can actually just use plain old calculus, and we get the right answer. So let's get started with our reading, and then we'll go through the text that he's got, and then I will do we'll do the computations together. Okay, so let's get started. So here it says, so in the case of discrete distributions, we saw that the maximum entropy configuration corresponded to an equal distribution of probabilities across the possible states of the variable. So that was like, when you had, let's say, when you had two options, heads or tails, the maximum entropy option is when the probability of both of those is 1/2. Because if it's, if one of them is 0.6, the other one's 0.4, then you're just going to be less surprised in one of the cases. You're often going to just see heads, and that'll your average surprise, the entropy, it will be less. So the maximum entropy when you have discrete, discrete set of options is just giving them all the same probability. Okay, so now let us consider the maximum entropy configuration for a continuous variable. So now he says, okay, well, it will be necessary to constrain the first and second moments of P of x, as well as preserving the normalization constraint. So moments are essentially, so they're just different kinds of averages. So the first moment of a random variable is, you could say m mu1 is P of x. The second moment is, x squared P of x, and so on. So that's just kind of a fancy name for that. The first moment is, we just call it the mean. The second moment is related to the variance, so we can equivalently constrain the variance, and that's what we're going to be doing. So let's have a look. So we end up with these kind of three different constraints. So we want to find the maximum entropy distribution subject to some information that we have on what the probability distribution can look like. And so let's have a look. So the first one just says, this is a necessary to be a probability distribution, right? So that's to be a probability distribution. Well, you have to be positive as well. It turns out we won't have to enforce that directly. But the other property that you will need is that you need to integrate to 1. So that's the first one. This is the information that we have. One of the pieces of information that the integral is, the average is equal to mu. So the mean info. And then this is the second moment information we have, that the average of the random variable subtracted from its mean squared, i.e. the variance, is sigma squared. So this is what's called the variance information. So now the question is, well, given that information, what probability distribution, what is the maximum entropy probability distribution? And so what we're going to use to figure that out is just use Lagrange multipliers. So this is a constrained optimization problem, and if you're familiar with how to solve those, you need to bring in this notion of Lagrange multipliers, and we'll go through this together. But the first step of that is to include the function you're optimizing, but then also include your constraint. So here's your first constraint. This is your mean constraint, saying that the mean has to equal to 1. Here's the second constraint, saying that the first one is that the probability has to integrate to 1. The second is that the mean has to equal to mu. And the third is this variance constraint. And we have, for each one of these constraints, we have a Lagrange multiplier that will be changing its values in order to enforce that constraint. And the way this works is what we do is we set the derivative of this function as with respect to p of x to 0, and we solve it, and then we use the derivative with respect to the Lagrange multipliers kind of give us the constraints. So we kind of juggle all of those equations together to arrive at the form of the solution. So at the end of all of that, which we're about to go through together, we end up with the very interesting observation that the maximum entropy distribution given a mean and a variance is actually the Gaussian. So that's pretty cool. So unlike you might have expected that it might be the uniform distribution as well, but actually it turns out that that is the Gaussian, and maybe we'll discuss some of that in a second after we read the computation. One important thing that he points out is that we didn't constrain the distribution to be non-negative, so we just kind of got that for free. Okay, so let's go now and try to just compute this maximum entropy distribution together. So we'll just go through the computation so you can kind of see how it's done, and we won't need to use the calculus of variation, at least not in this case. Okay, so let's go over here. So what's our job? So our task is going to be to, let me change colors here. So what we need to do, we need to maximize over minus p of x ln p of x dx. So that's our entropy. So this is this is entropy. And now subject to, well, let's just say such that we have 1. So this is minus infinity to infinity. So this is we'll just say this is because it's the probability distribution. The second one is we need the mean to equal mu. So this is our mean information. And the third was our variance information, right? So this was, let's integrate x minus mu squared p of x dx, and this is supposed to equal to sigma squared. Okay, so we have an objective function here that we want to maximize over p of x, subject to these 3 constraints. And I guess what we should probably say is maximize over p of x. So what is the thing we're maximizing? So we need to come up with this distribution. And indeed, when you want to come up with functions, generally the tool you have to use is the calculus of variations that kind of deals with the function kind of as a whole to some extent. But here we're just going to use, well, let's get there in a second. So first we're going to form our Lagrange multiplier. So sorry, our Lagrangian. So that Lagrangian is a function. It's going to be a function of p. So our p is now this function p of x, and there's going to be some Lagrange multipliers that are going to be enforcing these various constraints. So first we're going to have the function we're maximizing. So this is p of x log p of x dx. And if I write ln or log, I mean the same thing, the natural logarithm. Okay, but now we're going to have some Lagrange multipliers that are going to be enforcing these various constraints. So I'll just write them, the sign that you write, because they're equality constraints, the way you write them doesn't really matter. So you could write this as, for example, the first one you could write as 1 minus in p of x dx, or you could write it as, put the integral first and go -1. It doesn't really matter. Okay, And now we're going to put in the second constraint. So I like to put the the target value first, and that's going to be x p of x dx. So that's our mean constraint. So that's the term accounting for that. And finally, we're going to have the variance term. So let's try that. So this is x minus mu squared p of x dx. Okay, so we have this big function, and it's not, it's not even a function of just, of the normal function we're used to, which are kind of function. All of these arguments would be, kind of, let's say, real numbers. Actually, one of these arguments is a function. So when we want to maximize over functions, that's typically the tool we use is the calculus of variations. But what I'm going to do here is I'm just going to pretend, well, kind of recall that these integrals are essentially the limits of what do they call, like Riemann sums, right? So like the integral of a function f of x dx is like the sum over I of f of xi delta as delta goes to 0, something like that, right? So what I'm going to do is I'm just going to treat p of x as I'm going to pretend that I have like an infinite number of real values. So instead of thinking of it as a function, I'm just going to think of it as having let's say 1,000,000 different points that I need to optimize. And I can optimize them individually. So let's try that. So let's get rid of this. So what I mean by that is I'm going to think of my p of x. So this is, here is x. Here is this p of x that I'm looking for potentially. And I'm just going to just think of it as a bunch of different values. And I'm going to optimize those as real values, as kind of as scalar quantities individually. And we'll see that actually that also gives the right answer here. So we don't have to use the calculus of variations. We can just kind of deploy this kind of approximation, or this idea inspired by an approximation, and we'll get the same answer. Okay, so let's just erase that. So the very first thing we need to do is I'm going to take the derivative of, so the derivative of this Lagrangian with respect to p of x has to be 0 at each x. So let's do that. So so here is, and remember, we're going to pretend that p of x is now just kind of one of those discrete values. So what's that going to do? Well, what happens when we apply it to one of these distributions? So let's just do it for the first one. So is equal to minus dp of x and let's actually just to make it like extra, maybe there might be too many x's floating around, I'll pick out one of the x values, right? So we're going to say, what is the derivative of this Lagrangian with respect to p of xi? Okay, so now that's going to, so this is, and there's going to be a bunch of other terms. So I'm not going to, let's just deal with this first one. So now what's this going to be? So this is just going to remember, this integral is like a big sum. So we'll just move this derivative inside. There's a minus. That's going to be dp of xi, p of x log px dx. Okay, but remember that, so p of x, most of these terms, except for the xi term, aren't actually going to involve p of xi. So all of these are actually going to disappear. So they're going to be 0 except for one of them, which is, so we're going to get is equal to minus d bp of xi at p of xi itself. And we can put this dx as well, because that's kind of like a little constant. It's going to drop out at the end anyway, but it can hang around if it wants. Okay, so then we just do the normal differentiation, and that's going to equal to minus log p of xi. So that takes care of this first term, minus p of xi times 1 over p of xi. Okay, and that's coming from the logarithm. So this cancels that, and we end up with, there's a dx hanging around. I might forget the dx, it will end up disappearing anyway. So it's going to be minus log p of xi minus 1. Okay, so that was just the contribution from this first term, the derivative of this term. But of course, we have these three other contributions to deal with. So let's deal with, I'm just going to put one box around that. And now we have to deal with the contributions from the various constraints. So let's do that. So it's going to be plus d of dp of xi. And now we've got our first constraint. So that's going to be of y1 times 1 minus the integral minus infinity of p of x dx. Right? And now we play exactly the same game, right? So the p of x, the differentiating with respect to p of xi picks out just exactly one value of this function, one kind of location of this function. So what we're going to get is this is going to equal minus lambda 1, because the 1 is a constant, so it disappears. So let's do that. So dp of xi, p of x dx. So we're going to pick out just one value, and when we pick out that value, it's going to be dp of xi, p of x I. There'll be a dx as well, but I'll drop it. I've dropped it above as well. And so now this is going to equal to minus lambda 1. Okay, so that's the entire contribution from the second term. So let's highlight. So we put a box around that. Okay, so now we've got the third term. Okay, so let's do that. So now we've got plus d of p of xi is lambda 2, and now this is going to be enforcing our mean constraint. So let's do that. So that's going to be mu minus, and now it's x p of x dx. Okay, and you're probably getting used to the pattern by now, so now we just bring it in. It's going to equal to minus lambda 2 minus infinity d dp of xi x p of x dx, which is going to equal to minus lambda 2 times, there will be an so it's just going to be a 1 basically. Xi times p of xi. So now it's just going to equal minus lambda 2 xi. Okay, so that's the contribution from the second term. So the derivative picked out the xi component of that integral, and then we just take the derivative, and it eliminates the p of x. Okay, so let's put a box around that. All right, and let's add our final term. So here is the variance constraint. Dx, it's all fitting in. Okay, so again, this is now going to equal to minus lambda 3 d dp of xi of x minus mu squared p of x dx. And now we're going to pick out again the term that we care about. So it's going to be d dp of xi minus mu squared p of xi dx. And so this is going to equal to minus xi minus mu squared. Okay, terrific. So we now have And I've dropped, there should be a dx hanging out there. I'm just going to drop all of those because they will drop out anyway. Okay, so now the idea is that we set this to 0. So first let's pool all of our let's pool everything we found first. So what we've got is that d of L dp of xi is equal to minus log p of xi minus 1 So that was the contribution from the first term. Then minus lambda, is that just, it's a minus lambda 1 indeed. And then there's a minus lambda 2xi. And then minus lambda 3 xi minus mu squared. Okay, so that's putting it all together. There would be a dx hanging out here as well. So now the idea is now we set this equal to 0. So that's where the dx drops, goes to, so all of this equals 0. And so now we just bring the log of px to one side. So this then implies that log of p of xi is equal to minus 1 minus lambda 1 minus lambda 2 xi minus lambda 3 xi minus mu squared. So now we have that our probability distribution is going to satisfy p of xi is the exponential of minus 1. I'm going to stop calling it xi, I'll just call it x now. Lambda 1 minus lambda 2x minus lambda 3 x minus mu squared. And if you check in the book, this is exactly the probability distribution that he gets. But now we have to sort out what these lambda 1s, lambda 2s, lambda 3s are. Okay, so we've got the general form, but now we need to make it specific. So the way we do that is by enforcing our constraints. So the very first one, so what we're going to do is we're going to compute some integrals, and we're going to then try to use those integrals to increasingly simplify the terms that we're getting. Okay, so the first one is that we need p of x dx to equal to 0. Oops, not to equal to 0, to equal to 1. Okay, so we need that to equal to 1. So that means that we need to integrate, this complicated thing. And that's going to give some relationship among these lambdas. So this isn't actually a hard integral to do. It's a kind of a Gaussian integral in the sense that it only has quadratic terms in x. So you could do it, but I just went and I asked Mathematica to do it. So here's what the answer gave me. So we've got, if you actually integrate this integral, you get, so x, this big term up here, dx is what? So it's going to be some complicated term that actually we won't have to deal with much. I'll just write it here. It's going to be x of minus 1 minus y1 plus y2, looks like. And I'm just looking up to my other screen that's got the Mathematica result in it. Minus lambda 2 mu times root pi over root gamma 3. Okay, this looks like quite a formidable thing. We don't want to keep carrying it around. I'm just going to call it, let's just call this, let's just call it z. Okay, so that's just, because we're going to see that again, so we won't actually have to deal with it much. So I don't want to kind of simplify it any further. Okay, so that was one. So that was our first constraint. We get some relationship among the lambdas as we see here. So this whole thing, which is a function of lambda 1, lambda 2, lambda 3, is supposed to, and sorry, all our parameters, one of the parameters is supposed to equal 1. So that kind of gives a relationship among the lambdas. Okay, so now let's put in the second constraint. So we've got x of p of x dx is equal to 1. And so now we know that, so that means x times, this crazy thing, dx is equal to 1, and this integral is actually equal to, if we ask Mathematica, it's going to give us this, it's going to essentially just give us z, so this z function, and I'm just kind of making sure it's everything is simplified, indeed. So it's going to be times minus lambda 2 minus 2 lambda 3 mu. I think that looks okay. And now on the bottom, what do we have? We have 2 times lambda 3. Okay, and now we have that this thing must equal to mu. So that's kind of the expression we get. But now, so this z we found out from above is supposed to equal to 1. So this just disappears, is equal to 1. So now we're reduced with this, oops, and I think I'm running out of pages here, so let me add another page. Okay, great. Oops. Where did it all go? Okay. Anyway, so we are here, and we found that this, so we have this expression, and so now we need to just solve this equation. So what does this become? We get minus lambda 2 plus 2 lambda 3 mu is equal to 2 lambda 3 mu. And so we just cancel both sides, and so this implies that lambda 2 is equal to 0. So that's great because it actually simplifies a lot of things now. So our first actual expression for the lambdas is that lambda 2 is equal to 0. Okay, and that actually has, we'll come back to what that actually means. But for now, just remember that lambda 2 is equal to 0. I seem to have reordered these pages, so let's just go back. It doesn't matter. So now we've got our third constraint, which was that x minus mu squared p of x dx is equal to sigma squared. Right, so that was our variance constraint. And we put in p of x, so this is, x minus mu squared times this thing. And again, I've asked Mathematica to do it for me. And so it says, and I have to be careful here, that, okay, so it's finally computed, and we've got the answer. So we get a factor of z hanging out in the front times, there's a lambda 2 squared, so let's say lambda 2 squared plus 2 lambda 3. And at the bottom, we've got 4 lambda 3 squared, and this is supposed to equal to sigma squared. Now, the very first thing we can eliminate is this y2 squared, which we know because it's 0. Z is equal to 1, is equal to 0, so that simplifies. And so what are we left with? We are left with a very simple equation that says that 2y3 over 4y3 squared is equal to lambda squared. We eliminate that. So we arrive at lambda 3 is equal to 1 over 2 sigma squared. Okay, so that's pretty great. So, and we've already got that lambda, and we've already got, let's see, so we've already got that lambda 2 we've already got is equal to 0. And lambda 1 we still need to determine, so let's just go back and we can plug it into our equation. So let's expand out z again. So z was z of lambda 1, lambda 2, lambda 3 mu was equal to e to the minus 1 minus lambda 1 plus lambda 2, which has disappeared actually. Let's just put it in. So it'll be plus lambda 2 squared over 4 lambda 3 minus lambda 2 mu all over root of lambda 3 times root pi. Okay, but some stuff simplifies for us right away. So this lambda 2 is gone. This lambda 2 is gone. And so we end up with we get something that says that e to the -1 minus lambda 1 is equal to, and this whole thing, remember, was equal to 1. So now we get is equal to root over root pi, right? And so we can just write this as root 1 over 2 pi sigma squared. So now we have, so this should start to look a little bit familiar. This is kind of the constant term in the Gaussian. Okay, and so now we basically have everything we need, because we can now go back to the form our probability distribution was supposed to take, which was somewhere around here. I have written it down. There it is. Okay, so let's copy it. Okay, so here we go. So now we can put this all in there. So nearly finished. So we got that this is equal to 0, so there's no dependence on lambda 2 and lambda 3, and so we can just write this out as is equal to exp minus 1 minus lambda 1 times exp of minus x minus mu squared times lambda 3, which is, and we just found out that e to the -1 minus lambda 1, which is this thing, is equal to the normalizing function. So what we end up with is the result that we were after. So our distribution is indeed the Gaussian distribution with mean mu and variance sigma squared. So that's it. So it was a bit of a tedious computation, but nothing very complicated. So we just had to, thankfully we had Mathematica here to work out a couple of integrals for us. But the point is that, given the mu information and the sigma information, and we needed to constrain our probability distribution, we found the maximum entropy distribution just by going through the Lagrange multiplier machinery is a Gaussian. So I hope you found that kind of computation at least a little bit helpful. Sorry about all the scrolling around, but unavoidable, with all these equations. But hopefully you figured out how to do it, and you can then kind of carry out other examples of it yourself. And basically, this comes up in inference when you're trying to come up with probability distributions that express your lack of knowledge under some constraints. So you have some pieces of information, and now you want to have your probability distribution essentially reflect maximum uncertainty given the information that you have. So you don't want to bias yourself towards certain values over others. You just want to say, look, I can't pick among any of the values subject to the fact that their mean is mu and their variance is sigma squared. So I think so I think that's it for the session. So I hope you learned something, and I will see you in the next one. Thanks.